Hello, my name is Caleb Freilich, and today I'll be presenting my Phase 3 climate modeling project for my Physics of Climate course, which investigates the impact of Arctic sea ice melt on amplified global warming. We'll explore the intricate connections between ice loss, temperature changes, and discuss the broader implications that it has on our climate. Here's a quick overview of what we'll cover. We'll start with the hypothesis and research context, then delve into the scientific background, discuss the dataset and the modeling framework, and the RCP scenarios that we analyzed, the results, and finally, we'll take a look at our conclusions. One of the most significant indicators of climate change is the rapid loss of Arctic sea ice. Our hypothesis focuses on how this loss will impact the Earth's energy balance and contribute to future warming. Specifically, we hypothesize that increased Arctic sea ice loss over the next decade will reduce surface albedo, amplify solar absorption, and enhance Arctic warming through positive feedback loops. This process will ultimately contribute to radiative forcing levels consistent with higher-end climate scenarios. Observational data shows a clear and concerning trend. Since the late 1970s, the summer minimum Arctic sea ice extent has declined dramatically from approximately 7.6 million square kilometers to just 4.3 million as of 2024. This loss is not just a symptom of warning, it is a driver of further climate change. The primary mechanism behind this is the ice albedo feedback. Sea ice is highly reflective with an albedo of about 80%, meaning it reflects most of its incoming solar radiation. When the ice melts, it exposes darker ocean water, which has an albedo of only about 10%. This leads to increased absorption of solar energy, further heating of the surface, and accelerating ice melt. This feedback loop has measurable effects on the planet's energy budget. Studies estimate that the ice albedo feedback alone contributes to radiative forcing equivalent to about 10% of cumulative CO2 increase since the Industrial Revolution. This makes it a major factor in amplifying global warming. As a result, the Arctic is now warming 2 to 4 times faster than the global average. This phenomenon, known as Arctic amplification, is increasingly driven by sea ice loss and its associated feedback effects. If the current trends continue, the Arctic will experience even more extreme warming, with far-reaching consequences for global climate patterns. With this hypothesis in mind, my analysis will focus on using climate model projections to quantify these effects under different emission scenarios, particularly RCP 6.0 and RCP 8.5. I've chosen to focus primarily on RCP 6.0 as it aligns with current emissions trajectories and reflects a significant but plausible level of climate change. I also consider RCP 8.5 as an upper bound case to examine the potential worst-case scenario for Arctic sea ice loss and its broader climate implications. By understanding the impact of Arctic ice loss on radiative forcing, we can better anticipate future climate conditions and inform policy decisions. The consequences of Arctic sea ice loss extend far beyond the polar regions, profoundly impacting the global climate system. Notably, it could accelerate global warming, with studies suggesting that an ice-free Arctic might hasten global temperature rise by as much as 25 years. Even current summer sea ice loss could contribute an additional 0.19 degrees Celsius to global temperatures. Furthermore, melting sea ice alters global precipitation patterns and extreme weather events, potentially increasing amplified El Niño events, mid-latitude cold spells, and more intense storms. The loss of ice also intensifies coastal erosion, threatening Arctic communities and ecosystems. In summary, Arctic sea ice loss is a global climate driver, and continued trends may lead to more rapid warming, disrupted weather, and worsening environmental consequences. Understanding these feedbacks is crucial for climate policy and future preparedness. To understand our findings, it's important to grasp some key concepts. First is Arctic amplification, the phenomenon where the Arctic warms at a disproportionately faster rate than the rest of the globe. This is largely driven by the ice albedo feedback we discussed earlier. Sea ice and albedo are tightly linked. Sea ice directly influences how much solar radiation the Earth reflects. When we lose ice, we lose reflectivity, leading to more absorption and further warming, creating a vicious cycle. Finally, we plan on using the representative concentration pathways that we discussed earlier, or RCPs, to model different climate futures. These scenarios, developed by the IPCC, range from very stringent emissions reduction, RCP 2.6, to a business-as-usual high emissions path, RCP 8.5. Our models focus on 6.0 and 8.5 to explore the impact under the intermediate and the high emission scenarios. Our modeling uses EasyGCM, a NASA-validated Earth systems modeling toolkit. As we mentioned, we're focusing on 6.0 and 8.5 from the RCP pathways over a long time frame from 1850 to 2100 using a detailed spatial grid, 36 by 24 associated latitude-longitude points. We specifically analyzed the Arctic Ocean basin using a defined mask to isolate this region in lat long. Our analysis strategy involved carefully weighting our metrics to account for the varying sizes of the grid cells in latitude-longitude and the proportion of ocean within them. We also looked at seasonal changes, long-term trends, and correlation between our key variables. The primary metrics that we examined included ocean ice coverage, sea surface temperature, surface air temperature, and planetary albedo. Let's start first by taking a look at the temporal variation in Arctic sea ice coverage. Looking at this temporal variation, we see a very distinct seasonal pattern in Arctic sea ice. It reaches its maximum extent in late winter and its minimum in late summer. The difference between the winter and the summer is dramatic, with a large portion of the ice melting each year. Importantly, the seasonal cycle is occurring against a backdrop of long-term decline in ice cover, particularly during the summer months. The graph on the right clearly illustrates this trend during different RCP scenarios and time periods. We also observed a lag between the air temperature changes and the ice response due to the ocean's ability to store heat. The key takeaway here is that Arctic sea ice is not only highly seasonal, but also experiences a rapid long-term decline, which has significant implications for our global warming. It's important to recognize that sea ice loss isn't uniform across the Arctic. Some regions, like the Central Arctic Basin, maintain a more consistent ice cover throughout the year. However, other regions, particularly the marginal seas like the Barents and the Chukchi, are much more sensitive and experience ice loss at a faster rate. The GIFs here visually demonstrate this regional variability swept across our time interval from 1850 to 2100. In our analysis, we didn't really look at that regional variation within the Arctic, but instead chose to look at the Arctic relative to global climate trends. Still, it's important to note that ice loss forms an uneven pattern across the globe, and the regional variation highlights the need for targeted climate adaptation strategies that address the specific vulnerabilities of different Arctic regions. Looking at the historical and projected trends, we see a concerning picture. Over the past century, we've already lost a significant portion of summer sea ice. Both the RCP 6.0 and RCP 8.5 project that this loss will continue, with the potential for near ice-free summers by the end of the century under the high emission scenario RCP 8.5. The graph on the left illustrates the decadal changes in ice cover for the winter and summer sea ice. As can be seen, summer ice loss is a primary concern, especially under RCP 8.5. But even winter ice recovery is being challenged by increased emissions, with the potential for a permanent shift in the system around 2050 using RCP 8.5. This is seen in the figure in the bottom right, which shows that pivotal shift in the rate of change of decadal minimum ice cover. The key message here is urgent. Both RCP 6.0 and 8.5 predict continued ice loss, and only significant emissions reduction can prevent an ice-free Arctic this century. Even a minor regression to RCP 6.0 would help by stabilizing winter ice loss and reduce the effects of summer ice loss. As we hypothesized, reduced Arctic sea ice will cause an increase in surface albedo. While the overall correlation is weak, our analysis reveals that it is strongest in the summer, as indicated by the higher R-squared values. This tells us that surface reflectivity is most directly tied to ice melt during summer months. We also noticed that RCP 8.5 exhibits slightly steeper slopes than the RCP 6.0 model, which signifies a stronger dependence of albedo on sea ice coverage. In other words, in the higher emission scenario, as ice retreats in the spring, the change in reflectivity is much more pronounced. This suggests a heightened seasonal feedback effect as more ice is lost under the RCP 8.5 model. As more ice is lost and albedo decreases, the surface air temperature increases. We notice interesting trends when correlating the ocean ice coverage to the median surface air temperature in the Arctic. As you can see in the figure on the left, there is consistent monthly clustering of Arctic ice loss with expected surface air temperatures. This clustering is fairly linear across years, decades, and centuries of data. On the left, we can see the shift of this clustering by year. In the white-gray region, we have the data from the past, prior to 2025, which is distributed towards the upper left portion of the image. The colored region shows the model predictions over the present century from 2025 until 2100. As we expect, the distribution shifts down and to the right towards lower ice coverage and higher median surface air temperatures. Essentially, decreased reflectance driven by the loss of ice further drives ice melt lower over time and critically increases the median surface air temperature in the Arctic. The key takeaway here is that as Arctic ice continues to decline, surface air temperatures rise faster. This highlights a compounding trend, reinforcing the urgency of climate action. Now that we know that ice coverage is linked to temperature change, let's take a look at the decadal shifts in both sea surface temperature and surface air temperature to understand how both global and Arctic temperatures are changing over time. First, it's important to note that both global and Arctic ocean temperatures show a consistent warming trend across all future decades under both scenarios. Warming is projected to continue regardless of the emissions scenario, thus it's really about controlling the rate of change in our environment. From the images on the left, we note that the Arctic Ocean's surface air temperature rises more sharply than global surface air temperature. That is consistent with the phenomenon of polar amplification, which we discussed earlier, where the Arctic warms at accelerated rate compared to the rest of the planet. Crucially, the warming under the high emission scenario, RCP 8.5, is significantly steeper. In fact, we project a doubling of ocean SAT, surface air temperature, warming compared to RCP 6.0 post-2050 under RCP 8.5. This highlights the profound impact that different emissions pathways have on the rate of Arctic warming. But our impact extends far beyond the Arctic. Under RCP 8.5, the global mean temperature is projected to rise by more than 30% over the remainder of the century, demonstrating the far-reaching consequences of high emissions leading to melting sea ice and decreased albedo. Finally, it's worth noting some additional context. Historically, Arctic Ocean's sea surface temperatures is only above freezing less than 25% of the time. However, Arctic Ocean sea surface temperatures are rising rapidly, with RCP 8.5 showing that approximately 40% of the months in the last decade will have a median SST above 0 degrees Celsius, a 13% increase in the present decade. Furthermore, surface air temperatures in the Arctic exceed the 2025 median SAT temperature 1.6 times as often, indicating a clear warming trajectory relative to near-term baselines. These statistics really underscore the significant changes already underway in the Arctic. As we noted before, Arctic amplification suggests that the Arctic warms at a disproportionately faster rate than the rest of the globe. And here we take a look at that theory with the data from our two RCP models by computing the rate of change in the surface air temperature and SST in the Arctic and relating that to the global rate of change. We call this ratio the amplification factor. And just as an example, an amplification factor of 2 means that the Arctic warms at twice as fast as the global average. Arctic surface air temperature is warming much faster than the global average, with amplification nearing 2 times by century end, especially under RCP 8.5, as can be seen in the bottom left image. This could be due to ice albedo feedback. Conversely, global sea surface temperature is rising faster than Arctic sea surface temperature, and this could be because the thermal responses of the atmosphere and ocean are different. The Arctic atmosphere is highly sensitive to radiative changes, while the Arctic Ocean's SST increase is moderated by ice melt and thermal inertia and freshwater input. From a policy standpoint, however, we should leverage detailed research, conduct additional analysis as needed to fill in the data gaps, so we can really understand these Arctic processes and how they impact long-term global climate. While what we've discussed is concerning enough, further global changes could potentially be correlated to ocean sea ice loss and albedo feedback. Whether those relationships are causal is a point for discussion. However, there is potential for the Arctic to upset more than global temperature trends. RCP results indicate a future with reduced cloud cover, a 6% drop under RCP 8.5, increased precipitation and evaporation, and more atmospheric water vapor, all of this allowing for more energy to enter and be trapped in our climate, compounding challenges that we face currently. Reducing emissions can help preserve Arctic sea ice, maintain albedo, and mitigate these harmful global and climate impacts, intensified warming, disrupted cloud patterns, and a more volatile water cycle. In conclusion, our modeling reveals several concerning trends. We've illustrated that the rapid decline of Arctic sea ice, especially during summer months, and the critical role of ice albedo feedback has an impact on amplifying Arctic warming. We've also seen that the higher emission scenarios project much more drastic changes to our global climate with potentially severe consequences. Given these findings, we recommend several key steps. First, we urge support for focused research to address the remaining uncertainties. This includes refining our regional climate models, investigating the links between Arctic change and mid-latitude weather, assessing the social impacts on Arctic communities. A lot of this work is already available. Thus, potentially forming an Arctic climate group to analyze these results could help identify where work can be leveraged to help inform these key trends. Secondly, we advocate for precautionary action. The potential for accelerated warming and irreversible tipping points necessitates a cautious approach. We should prioritize policies aimed at significant emissions reduction, aligned with lower emission scenarios, even as we continue to research. Finally, international cooperation is essential. Addressing this complex issue requires coordinated efforts in research, data sharing, and policy development among Arctic nations and the global community. While nothing in life is guaranteed, following steps like these can help ensure that we have the knowledge and capacity to respond effectively to the challenges posed by Arctic sea ice loss and its global implications. Thanks for listening to my presentation. I hope you take away something useful from this work. If anything at all, I hope you have a broader appreciation for the interconnectedness of our climate and the broad impact that subtle changes can have. If you have any questions, please reach out. My contact information is on the screen. Thanks.